Welcome to AI Paperslop, where we summarize the latest AI and tech papers so you can get the core signals out of all that machine learning noise.
Yep, glad to be here.
So we are jumping straight in today. The paper is called DreamWAM, and it's subtitled Beyond RGB Future Prediction for World Action Models.
Right, and this comes to us from an incredible group of researchers at HUST, Robotics, Wuhan University, and Horizon Robotics.
Yeah. So I want to give you the executive summary right up front. If you are building robotic policies, current world action models or WAMs, they basically predict future states using only RGB pixels.
Which is, frankly, a massive bottleneck.
Exactly. It's a fatal flaw because it entangles your actual task progress, like a robot arm moving toward a cup with totally useless visual noise, like a shadow moving or the lighting changing.
Yeah, the model gets confused by things that don't actually matter.
Right. So DreamWAM solves this by forcing the model to, quote-unquote, dream across 4 explicit dimensions during training.
4 distinct views of the future.
Right. Appearance using standard RGB, motion via optical flow, geometry using depth maps, and semantics using Dino V2 features.
But the absolute kicker here, and the reason you should really care if you're deploying these models, is what happens at inference.
Yes. This is the best part. At deployment, all those extra pathways completely disabled.
Poof, gone.
Gone. You get a massively more robust policy. We're talking jumping from a 55.6% success rate to 74.4% on real-world visual perturbations. And it has 0 extra latency, 0 extra sensors, and 0 extra compute at the edge.
I mean, for anyone building predictive control systems or, struggling with edge compute limits, that takeaway is just fascinating. It goes way beyond just listing what the model predicts.
Right, it's about the architecture.
Exactly. The real engineering marvel is how they actually integrate these super heterogeneous features into a diffusion backbone without, completely destroying the pre-trained video priors.
It really is a masterclass in architectural routing.
Yeah, it forces us to totally rethink how we supervise physical understanding in visual models.
So let's unpack the baseline architecture first, just so we understand why current models are hitting this wall.
Sounds good.
Because if you're training robotics policies today, you probably know how standard WAMs operate. They don't just map a single current image directly to a motor action anymore.
No, they try to anticipate.
Right. They anticipate how an interaction is going to unfold by generating a video rollout of the immediate future.
Basically predicting the next few frames of video.
Yeah, and then they feed that internal future representation into an action expert to derive the final policy.
Which sounds great in theory.
Right. But the critical issue is that we've been forcing these networks to imagine the future purely as a sequence of colored pixels.
Yeah, we've essentially been treating future prediction as just a video generation problem.
Mm.
But for robotics, it desperately needs to be a state evolution problem.
Yeah.
Like when you optimize a model purely on an RGB reconstruction loss, you're basically forcing the loss landscape to treat all pixels equally.
Right, which makes no sense for a robot.
Yeah. Exactly. The network spends just as much gradient energy trying to perfectly predict, like, the reflection of a fluorescent light on a table as it does trying to predict the precise displacement of the coffee mug you actually want to pick up.
It's crazy.
The model just doesn't inherently know that the mug's location is the critical state variable, and the reflection is just a nuisance variable.
It's like, okay, imagine trying to learn a manipulation task purely through RGB. It's like trying to learn the rules of chess, right? But you get hopelessly confused because today the board is made of marble instead of wood.
That's a great analogy.
You're entangling the task-relevant state, like, the knight moving in an L shape with a totally arbitrary visual realization of the scene.
And when you take that marble chessboard into a new room with different lighting, the model completely forgets how the knight moves.
Just totally breaks down.
Yeah, that failure during out-of-distribution or OG day generalization, it happens because the policy organizes its internal representation strictly around appearance.
It overfits to the visuals.
Right, it overfits to visually salient details. If you change the lighting or swap the background, the entire RGB pixel distribution just shifts drastically.
And so the video rollout gets messed up.
Exactly. The anticipated video rollout degrades into all these weird artifacts. And because the action expert relies entirely on that rollout to decide what motor torques to apply, the whole policy just collapses.
Even though the physics haven't changed.
Exactly.
Yep.
The actual underlying physical state transition hasn't changed at all. A knight still moves in an L shape.
Right.
But the model just lacks the inductive bias to separate the physics from the pixels.
Okay, so To fix this, the authors argue that a machine's dream of the future shouldn't just be what it looks like. It needs to represent the dynamics, the spatial organization, and the semantics.
Which brings us to the 4 views.
Right. They deconstruct the future into these 4 complementary views. First, appearance, which is your standard RGB, encoded via the WAN 2.2 video VAE.
Yeah.
Second is motion, where they make the temporal change explicit using optical flow from a RAFT model.
Which is super important.
Third is geometry, capturing the spatial organization using depth anything V3 or DA3. And fourth is semantics, preserving the object consistency using Dino V2 patch features.
And it's worth noting that these 4 views, they aren't meant to represent some complete perfect simulation of reality.
Right. It's not a physics engine.
No. They serve as highly correlated projections of an action-relevant future. They are explicit training targets that are derived entirely offline from the training videos.
Right. So you run these big models offline first.
Exactly. Like the RAFT model calculates dense optical flow fields by measuring the exact vector displacement of pixels between adjacent frames.
Just pure movement data.
Yeah. And Dino V2, it processes images as patches and learns semantic representations that are just incredibly robust to visual noise.
It knows what the object is, basically.
Right. It doesn't care if a strawberry is lit by a warm tungsten bulb or a harsh LED. Its patch-level attention recognizes the core, strawberryness of the object.
Okay, but wait. I have to push back on this premise a little bit. On behalf of the engineers listening who, prefer elegant, minimalist architectures.
Sure, yeah.
Are we just overcomplicating the pipeline here? Because mathematically speaking, a sequence of RGB frames theoretically contains all the information you need to infer motion and geometry and semantics.
Technically.
Right.
Yeah.
Like, if the depth and the flow are already implicitly captured in the pixels, why are we forcing the network to look at them separately through all these heavy external models during training?
Well, the crucial distinction here is between information presence and information extraction.
Okay.
RGB absolutely contains those cues, but an RGB-only objective, that doesn't provide any guarantee that the neural network will actually disentangle those cues into a useful, robust, latent manifold.
It might just find a lazy shortcut.
Exactly. By explicitly supervising the network with optical flow, depth maps, and Dino features, you are dramatically reshaping the loss landscape.
You're forcing its hand.
Yeah. You heavily penalize the model if it doesn't care about what objects are involved, how they're moving, and where that change is occurring in 3D space.
Right.
You're injecting a structural inductive bias. You're explicitly commanding the model to preserve the physical structure of the scene instead of just making the next frame look photorealistic.
Got it. So you're forcing the latent space to organize itself around physics and semantics, not just, pretty textures.
Exactly. Yeah.
But man, this introduces a massive architectural headache.
Oh yeah, huge.
How do you shove Dino features and optical flow and depth maps into a standard video diffusion model without completely breaking it?
It's tricky.
Because the backbone here is the FastWAM architecture, right? Which uses a video die to model the future and an action die to output the policy. And both networks share attention layers.
Yeah, that 2-expert architecture is the foundation.
Yeah.
The video die models the future video latents, while the action die denoises the action trajectory. And because they exchange information through those shared attention blocks, the action die's tokens can attend directly to the video die's tokens.
Oh, I see.
So if the video die is structurally aware, the action die gets this massive, totally free upgrade in its spatial and physical reasoning.
That's super clever.
But yeah, the real dilemma is how to actually introduce these new heterogeneous targets into the video IT during the training phase.
Right, because if you take Dino embeddings and DA3 depth maps and you just concatenate them directly into the main diffusion stream right alongside the RGB.
Oh, it would be a disaster.
Yeah, you're going to catastrophically wreck the pre-trained video generation priors of that WAN 2.2 backbone.
Absolutely. Because that VAE latent space was trained exclusively to reconstruct RGB. Features and depth maps, they have wildly different variances, spatial correlations, and statistical properties compared to RGB latents.
You don't speak the same language.
Not at all.
Yeah.
If you force the backbone to model them through the exact same denoising MLPs as the visual data, you basically shift the internal activations entirely out of the domain the pre-trained video prior expects.
You just scramble its brains.
Pretty much. So the authors bypass this by designing a dual pathway system. They split the routing based on the specific nature of the target feature.
Okay, so let's break those down. The first path is joint denoising, and they reserve this specifically for the motion data.
Right. So motion, specifically the optical flow, it actually shares a very dense spatiotemporal structure with the RGB data.
Because it's pixel to pixel.
Exactly. Because the flow is estimated between adjacent frames and can literally be encoded by the exact same video VAE, it essentially lives on the same latent grid.
Okay, so they play nicely together.
Yeah. DreamWAM leverages this alignment by just concatenating the RGB and motion latents along the channel dimension. They're then jointly denoised at the exact same flow matching time step. So they become part of the primary denoising stream.
Okay, that makes sense for motion. But for geometry and semantics, they use a completely different mechanism, which they call gated residual branches.
Yeah, this is where it gets really elegant. Because DA3 depth and DNOV2 features, they come from external encoders and operate in completely different feature spaces.
Right.
So they are kept entirely out of the main denoising stream. Instead, they're introduced via these lightweight gated residual branches that attach only to selected video DOT layers.
Oh, so they don't corrupt the main flow.
Exactly. During a forward pass, the main backbone state remains completely untouched. The depth and deno pathways calculate a view-specific residual, which is essentially just a proposed correction to the latent state.
And the gated part of that is critical, right? It's basically a learned parameter that controls the magnitude of that correction before it adds it back to the main state.
Yes, and these gates are typically zero initialized.
Meaning they start out turned off.
Right. The very beginning of training, the residual branch contributes nothing, meaning the original video prior is entirely unharmed.
Ah, that's smart.
Yeah, and as training progresses, the gate slowly learns to weigh and add its semantic or geometric delta. It refines the pre-trained video representation through these highly controlled additive corrections, rather than trying to, replace or override the main processing loop.
And we actually have the ablation studies to definitively prove why this specific routing is so necessary.
Oh, the ablations are fascinating.
Yeah, the authors tested a variant where they routed everything, depth and semantics included, through full denoising. They called this DDD routing.
And what happened?
Well, when they forced all 4 views into the mainstream, performance just plummeted. It actually dropped below the standard RGB-only baseline.
Wow.
Yeah. But when they used the proposed hybrid routing, so denoising for motion, and residuals for depth and semantics, which they call DRR performance on the LIBERO benchmark, surged to an incredible 98.90%.
I mean, that ablation proves perfectly that simply throwing more auxiliary objectives at a model isn't enough to induce physical understanding.
You can't just mash it all together.
Right. The routing mechanism, really respecting the representational form and the statistical distribution of the target, is the only way to unlock that performance without inducing catastrophic interference.
Exactly. Now, here's where it gets really interesting.
Okay.
Because if you are an ML engineer trying to squeeze this massive policy onto a tiny onboard compute module on a robot, you're probably hyperventilating right now.
Yeah. Thinking about running WAN, RFT, depth, anything, and Deno all at once.
Yeah, running all of that simultaneously on an edge device sounds impossible. But here is the brilliant part. At inference time, almost all of it vanishes.
Just gone.
Yep. The RFT, DA3, and Dynovade2 encoders are entirely removed from the pipeline. The residual branches and feature prediction heads inside the network.
Yeah.
Disabled.
So you basically just deploy an architecture that looks almost identical to the baseline FastWAM.
Right, but wait, I have to stop you there. Because we just said the motion pathway was concatenated into the main denoising stream.
Yeah, we did.
You can't just drop an input channel from a trained neural network and expect it not to, hallucinate garbage. What about covariate shift? I mean, if the network expects 16 channels and suddenly half of them are missing, how does it not just collapse?
So mechanically, it's actually really simple. The optical flow input channels are literally just filled with zeros.
Wait, really? Just zeros?
Yeah. If you look at the matrix multiplication in the first projection layer, feeding a zero tensor means those specific flow channels make zero direct numerical contribution to the video IT input at inference.
But why doesn't that zero tensor cause a massive distribution shock to the network?
Because of how the network adapted during the joint denoising training. Remember, the primary RGB latents still carry the bulk of the environmental signal.
Right.
During training, the weights applied to the motion channels were optimized to treat that flow data as a correlated target. The network essentially learned to pull structural priors from the RGB itself to predict the flow.
Oh, wow. So it internalized it.
Exactly. It internalized the physics into the RGB processing pathway. So when the flow is zeroed out at inference, it acts as a neutral baseline. The matrix multiplication nullifies the external motion pathway's contribution, leaving the newly robust, structurally aware RGB weights to do all the heavy lifting.
That is insane. That is the holy grail of representation learning right there.
It really is.
You use heavy, multimodal training compute, but it results in a lightweight, highly structured inference pass.
Yep.
You feed it standard RGB video. It runs at the exact same inference speed and latency as the baseline FastWAM model, but the internal latent representation it generates is just drastically more robust.
You're getting a massive capability boost essentially for free at deployment.
Free lunch.
Yeah.
So let's look at how this structural awareness actually translates to performance, starting with the simulation data on the LIBERO benchmark.
Right, the simulation tests.
Specifically, they used the LIBERO-Plus dataset. This tests out-of-distribution perturbations. So they throw unseen camera viewpoints, completely new lighting conditions, and different object layouts at the policy.
Which is really the ultimate test to see if the model actually learned physics or if it just, memorized a specific sequence of pixels in the training set.
Exactly. So in the joint inference setting, where the model predicts both the future video rollout and the action, the standard RGB-only baseline achieved a 69.16% success rate across these unseen shifts.
Okay.
DreamWAM pushed that success rate to 75.47%.
It's a huge jump for Ode.
It is.
Absolutely.
But what I found incredibly revealing is that they also tested a no rollout version.
Oh, yeah, this is so cool.
Yeah, this is where they don't even ask the model to generate the future video at test time. They just pass the current frame through the backbone and directly predict the action.
Right.
And even without explicitly imagining the future video at test time, the model trained with the DreamWAM framework jumped from 51.36% to 63.44% on the perturbed benchmark.
That no rollout improvement is just profound for understanding what the model actually learned.
Yeah.
Because it proves that the structured future supervision doesn't just act as a trick to, improve video generation quality. It fundamentally strengthens the underlying policy.
It makes the action expert smarter.
Exactly. Because the action DIT and video DIT share those attention layers, the action expert learns a significantly better mapping. The representation it trained against was structurally and geometrically sound.
So even if you don't generate the video.
Right, even if you skip the video generation step at inference, the cross-pollination of those feature spaces ensures the action tokens are grounded in a real physical reality.
Okay, so the simulation proves the architecture works mathematically right. But the real test of those entangled nuisance variables, like the shadows and the reflections we talked about at the start, that can only really happen under actual physical lighting.
Right. The real world is messy.
So how did it handle the real-world Agilex Piper dual-arm robot?
Well, they tested 4 tabletop tasks: dish stack, dual object pick, strawberry selection, and block stack.
Okay.
And to really isolate robustness, they took the strawberry selection task and subjected it to severe visual distribution shifts. They kept the language instruction, the target fruits, and the success criteria identical.
Yeah.
But they heavily manipulated the physical environment.
Yeah, they really mess with it. They added random colored background patches to the table. They physically shifted the fill lighting to cast completely new, totally unpredictable shadows.
Just trying to break it?
Yeah, and they threw task-irrelevant distractor objects all over the workspace. Under these totally chaotic conditions, the baseline FastWAM model managed only a 55.6% success rate. It failed almost half the time.
Which is pretty standard for these models.
Right. But DreamWAM crushed it with an average success rate of 74.4%.
And the failure modes of the baseline in this real-world test are incredibly telling, I think.
Oh, absolutely.
The authors highlight this specific failure case for the RGB-only model.
Mm-hmm.
The robot would navigate perfectly toward a strawberry, right?
Mm-hmm.
But when it came time to place it, it would close its gripper right beside the plate, completely missing the target.
Like just grabbing thin air.
Yeah. It didn't fail to understand the task. It entirely lost track of the spatial relationship between the gripper and the plate. And why? Because the surrounding pixels, the background color and those new shadows, had changed the local gradient of the image.
It literally couldn't see the plate for the shadows.
Exactly. But because DreamWAM was explicitly forced to predict geometry and motion targets during training via those residual branches and the joint denoising, its internal representation prioritized spatial relations.
It had that depth map baked into its brain.
Right. It intrinsically knew where the plate was in three-dimensional space, regardless of the visual clutter, because its weights were optimized to care about depth and temporal displacement, not just matching RGB textures.
I mean, we are really looking at a paradigm shift in how we formulate world action models for robotics here.
I completely agree.
By moving beyond simple RGB reconstruction and introducing this structured multi-view training, forcing the model to care about motion, geometry, and semantics, we get a policy that truly understands the state of the physical world.
Yeah.
And because of that brilliant architectural routing, you get all of this robustness with a zero overhead RGB-only deployment.
And, this raises an immediate massive question for the future of predictive control.
Oh, what's that?
Well, if enforcing spatial and semantic consistency makes a visual network this much more actionable, what happens when we extend this exact routing framework to non-visual modality?
Oh, wow.
Right? Imagine a world action model that dreams the future tactile feedback of a slip. Or maybe it anticipates the specific audio frequency of a snapping mechanism.
Using the exact same gated residual branch.
Exactly. Using those during training only to drop those sensors at inference. We are rapidly moving from models that just hallucinate pixels to models that natively simulate physics.
Imagine a model hallucinating the precise sound of a successful grasp before it even moves the arm, allowing it to adjust its torque based on an auditory dream.
It's incredible.
It is a wildly exciting direction for the field. Well, if you want to dig into the tensor mechanics or deploy the architecture yourself, the researchers have publicly released the code and models on GitHub, which we highly recommend checking out. Until next time, keep optimizing.